Hello. So the first slide is wrong. I didn't update it to fit the title, but the main thing I'm going to talk about is about how some simple old fitness landscape can be shown to emerge from more wider assumptions, but not only that, and also how this kind of properties of this landscape can be can reconcile both mutant data, fitness data, and long-term fitness trajectories, which are, I think, not well consistent right now. So first, okay, okay, I'll do like this. Okay, you see next slide now? Okay, so first, there is a wealth of data on random mutants and their fitness. And the reason is that the most easy mutants to gather is a random mutants, most of which are deleterious in most environments, because we don't have any, because beneficial mutants have to be first sown out of all the mutants before we can get them, whereas there are a diversity of methods to produce random mutants and measure their fitness. So either by bulk sequencing of many tagged mutants or by head-to-head competitions, there has been a variety of measurements of those patterns, mostly in microbes, but even also in Drosophila. And they seem to be, so with a variety of tests done on models that describe the patterns in question. And they seem to be consistent with a global, an overall view of optimum theory, or at least a substantial amount of those papers testing it have seen consistent, more or less quantitative tests, have seen consistent patterns with a view that there is an optimum and that phenotypes are under stabilizing selection for this optimum and mutants are just random movements in this. I'll detail that later. So part of it is the shape, the overall gamma-like shape of the random mutant fitness, especially when in mild conditions where there are no beneficial mutations. Also, when we change the environment, so here it's a nice Yetpass paper where they measure the fitness effects in yeast, in one gene of yeast. When we change the environment to more harsh conditions, the shape changes and it tends to be an increase in variance, an increase in skewness, a decrease in skewness and increase in variance. And the overall pattern actually of change in variance, skewness, and mean can be tested. So this was a review we did over 14 different mutant accumulation data sets to check if it was consistent with a simple optimum view and more precisely with even a quadratic fitness function relating phenotype and fitness. So there are some tests like this. There are also a very nice experiment by Perfetto, Isabel Gordo's group, where they tested whether going a bit beyond that, whether when you use random mutant data and then you readapt the mutants to the environment so that they compensate for the deleterious mutations, the adaptation profile, depending on the initial fitness, that was the first statement that the adaptation rate depends, is proportional, negatively proportional to the initial fitness. And in a way that was consistent also with optimum views and more precisely with a particular form of Fisher's model. So the thing is that the reason people have tested this, I think most people have talked with, is that optimum view of adaptation is at the core of a lot of things in evolutionary ecology. It's at the core of the niche concept of a lot of evolutionary quantitative genetics with stabilizing selection and traits. And it is maybe the only model used in evolutionary ecology because we can conceptualize what an environment does on the distribution of fitness effects using this. So it's been used in range expansion theory, in adaptation to changing environment, moving optimum, all that. And it's hard to handle those environmental variation effects on adaptation without this notion of optimum. At least it's not done a lot. But on the other hand, the long-term fitness trajectories from the most famous and the longest one in Rich Lenski's lab has recently changed its message because the early dynamics that you can see here, they were consistent with a basic climbing hill view where you adapt and then you saturate, fitness saturates around an optimum. Well, there's no optimum for fitness, but fitness saturates because you've reached an optimum. And now the more recent data over much longer term are not so consistent with this anymore. And the fitness seems to be increasing ever and ever and ever. So how do we reconcile this data set, which is, of course, it's one experiment, but it's maybe the most best documented adaptation trajectory data set. So it has a weight, and it's a very, it has a power for testing it because it has a lot of information in it. And those previous, well, other experimental data sets. So getting back to the optimum view, so what is called Fisher's geometrical model, which is really, there's a general version of Fisher's geometrical model, which is really this view that there is an optimum and that mutation is a random movement in it. And I'm going to talk about one that has been used mostly in evolutionary ecology, which is the one where the fitness function relating traits and fitness is quadratic, in at least Malthusian or Gaussian when we look at Darwinian fitness, and mutant effects that are here. So here you have phenotype, 2 traits, for example, fitness here, and that's the optimum. And you have a wild type somewhere that mutates and does a random displacement. And the assumption usually used, so you can calculate mutation effects with this, etc. And the assumption usually used that you have n arbitrary traits, and there's a quadratic Gaussian fitness, and mutation effects are normally distributed with a mean 0 and some variance covariance matrix. Here it's an anisotropic version because it's not circles, it's ellipse. So some traits are more influent than others. Now, this has been tested in several cases. On random mutant data and a few things. And it seems to have consistent patterns, sometimes more or less quantitative, with various quantities like the DFE shape across environments or epistasis, etc. It doesn't mean that it's a fully, first, it's clearly not accepted widely as a model. And second, the tests, there aren't so many that are very quantitative anyway. Some are quite quantitative, but it's often considered as just heuristic and not useful for actually predicting, for example, adaptation, because its assumptions are very simple. And so one question I will ask is, are they so simple, or are they simple, or do they emerge from much less constraining assumptions? And also, well, can this kind of model, Fisher's model, be reconciled with those trajectories, which are not, seem to not saturate? So the goal is multiple. First, I'm going to talk about an old paper from 2014, where I tried to make Fisher's model emerge from much wider assumptions. Second, I'm going to try to fit whatever comes out of this on trajectories of fitness in the LTE, the long-term experiment. And third, to see if the resulting kind of parameter estimates are consistent with mutant data from this same experiment. So first, the general model. So I tried to not use any precise distributional assumptions, but more try to look for what are the minimal set of assumptions that basically generate this kind of models and this kind of DFE shapes and all that. So first, pleiotropy. There is many phenotypes that are jointly affected by each mutation. So that's really not crazy from a lot of measurements of single mutant effects on microarrays, expression data, various pleiotropy information. Second, I will consider weak unbiased mutation effects on basic phenotypes. So weak meaning it's a local approximation around the wild type phenotype. And unbiased means I consider that they tend, over all the many phenotypes, they tend to have a mean of 0. So the reason is that the DFEs don't look like ones that we would expect if there was a bias, but also because it's this version of the model that is used a lot. So, and also the data, again, on single mutant effect on enzyme activities or things like that, tend to go towards those kind of unbiased mutation effects. Third, I will consider phenotypic integration, in that there are many traits that are modified by a single mutation, but then they are integrated into the organism to produce fitness, to cause fitness. And this integration involves a loss in the number of independent traits that affect, not fully dependent traits that affect the system. So basically, if you have 10,000 phenotypes modified, the system in the end will look like if there was, say, 10 not fully correlated traits. So it's like the degree of freedom of fitness is not the same as the number of pleiotropically changed traits. So there are a distinction between mutation and fitness on the dimensions. And third, I will use the idea that the wild type is close enough to an optimum that we can do a local approximation around this optimum. But there is no assumption on distributions of the effects or on what's inside the phenotypic integration. Not too much, it is no particular distribution. So maybe a graph to summarize this. So there's a genetic mutation that hits a phenotypic network of whatever it is, metabolic, regulatory, developmental, for multicellular. There's a network, but we don't want to specify which. And this affects a set of P traits that are P for pleiotropy, that are mutable traits. So they are modified by the mutation to some new value. So there's pleiotropy. It's a general distribution with finite moments, that's all. So the same kind of assumptions that we use for central limit theorem. And it's unbiased, so E of dx is 0. Then there is phenotypic integration through what I call developmental function, which is, there is a development even in a cell and multicellular. And this modifies a set of smaller number of traits that affect directly Malthusian fitness. So these traits may be part of this. Basically, these are the degrees of freedom of fitness, meaning that, in fact, fitness is caused by a linear combinations of all these, which end up being like N traits, not P traits. So, and this Malthusian fitness, false assumption, is around an optimum. So the key approximations we use to do that from that is first, near any fitness optimum, near this function M of Y, there is always a single unique basis in which to write the traits, where you can write it like this. So an isotropic quadratic fitness function. So this is the Morse lemma, but it's really a Taylor series around an optimum. It's important because phenotypes in itself do not have a true meaning. You could take the log of the activity of an enzyme or 1/(square root of this activity divided by its affinity for another. But if you consider that there are many bases in which to write phenotypes, there is just, for a given basis you use, there is just one single basis where you are isotropic. So you have now narrowed down those traits. They are not biologically meaningful in itself. You just choose the combinations where it is an isotropic, where it is isotropic for fitness. So this function. Second, mutations have a mild effect. So it means that from traits Y, from traits X mutated to traits Y, there is a Taylor series we can make so that the change in trait Y is just a linear combination of change in initial traits. And there we will have a set of coefficients that are many, many coefficients, N times P matrix, with all the effects of traits mutated on those Y traits, those final traits, optimized traits, I call them. So these are like pathway coefficients. They are everything that affects make mutations change. And now we use two large number approximations. First, the central limit theorem. So this emerges quite readily. If B is filled with whatever things which are not too many zeros, then whatever distribution you put in X, if you do a linear combination of many traits, you end up with a normal distribution of the traits Y, just because they are caused by the first ones and they are averaging many, many effects of many, many pleiotropic mutations. Of many, many pleiotropic effects of a single mutation. So then you have a matrix formulation for the variance covariance matrix of this trait, but you already get Gaussian traits just out of pleiotropy, basically. But this matrix formulation is complicated because you have the variance of the mutation covariance matrix on mutable traits, and you have all the partial coefficients. And those can be whatever, and we don't really know them. And they can even change randomly through life. So here, the second central limit, the second large number approximation is the random matrix theory, which is the study of matrices that are filled with random terms. And there are several results and tools, and it's, I think, underused in evolutionary science, but it yields very simple outcomes on what happens when you fill in the coefficients in B and V with random values from any distribution. And the outcome is a Marchenko-Pastur distribution of the eigenvalues of this matrix. So these are the eigenvalues of the matrix, M, so the mutational matrix. So this tells you those Gaussian mutant effects, are they in ellipse or are they in circles? And that's quite important. So that's the distribution you get, and you can use various distributions to fill in your coefficients, and you still converge to the same distribution. To converge, you need a large P and a substantial N. But random matrix has this property that it's fairly robust and converges quite quickly. So it works with a limited number of traits. So here you see how phenotypic integration now yields isotropy, because if you have a lot of trait P and a few traits N, then this ratio, which is the key shape parameter of the Marcinko-Pasteur, becomes very large. And as this ratio becomes large, you narrow your distribution of eigenvalues around a single value. So basically, from an ellipse, you narrow to a circle. And so it means integration implies that if you have many pleiotropic traits and a few traits that determine fitness, you end up with actually an isotropic Fisher model. But now, this is true when you fill in the coefficients B here with unbiased coefficients. When you add a bias in the coefficients, so you fill it in, but you have no reason to say that the average of the coefficients are 0. So if there is a bias in the coefficients, there is a very exotic phase transition that occurs from a nice theorem from Benaish-George and Nadakouditi 2011, I think, that says that whatever can happen is only that all your eigenvalues that are represented here, they will tend to be narrowed around, to be scattered around 1, but one leading eigenvalue only will tend to deviate as the coefficient of variation of those coefficients here becomes smaller and smaller. So as you bias your distribution more and more, first you see no effect, and then you start to have a leading eigenvalue. So it means that you go from balls to ellipsoids like this. And that's important because you start to include anisotropy, and it emerges from this particular property. So basically anything can happen from having isotropic model or anisotropic, but then with only one driving direction. Okay, so I'll now switch. So it means that we can fit these distributions of fitness effects are from those this model, they are explicit, so we can use them to fit the data. And it also has interesting implications for parallel evolution, because if, for example, you are with an ellipsoid like this, an environmental change that leads to a new optimum around here will tend to favor whatever mutations that are in this direction, in particular genes. But if you change to an environment that is here, you will not favor particularly this direction. And so it means that you can have some environments where there is parallel evolution, some where there isn't, or where different genes are involved in the parallel evolution. So that's, I think, quite interesting because it's flexible. Now, from that, we have a model of the distribution of fitness effects, and it has this, the only thing we can do with the Fisher model is allow it to have one dominant direction. Now from that, how can we plug in this model into a model of fitness trajectories? So going from mutation effects distribution to a fitness trajectory requires to handle mutation, selection, and drift minima in asexuals. So we can't use the infinitesimal limit. So there are difficulties with this that I've hit on since my PhD probably, yeah, because Fisher's model has deleterious mutations and does not necessarily lead to low polymorphism. So the classic clonal interference model, which is, for example, used in Weiser, is not necessarily a good option because all those deleterious mutations are simply ignored, and that's not always accurate. Also, the regimes of large populations are easily more polymorphic where we cannot use the simple clonal interference model. It depends on the parameters. Second, of course, clonal interference models are made for stable DFEs, stable distributions. They can be updated to handle epistasis where the wild type changes, and as it changes, the distribution of effects changes, but it's not so easy. And that's the second problem. There's pervasive epistasis. So we can't use, for example, what has been derived expressly for highly polymorphic populations, which are the traveling wave models. We don't use them, at least the way I know them, because they assume stationary regimes, and with epistasis, there isn't. So we can't either use this tool. But on the other hand, those models with diminishing return epistasis, they tend to have a stabilizing effect on fitness distributions so that we can, in fact, often ignore drift, and that makes things much simpler. Then we can use deterministic models. So that's what we derived in previous work. So we basically use a model of on the expected generating function of the fitness distribution. So we ignore drift, partly, but it will also take an expectation. Anyway, that leads to a dynamic of mean fitness. And we have derived one or other models for the isotropic FGM, and the other paper is for the anisotropic case. So now, from this, what does it give us? We get a fairly simple trajectory that we expect for Malthusian fitness minus the initial Malthusian fitness, the mean Malthusian fitness across populations and within populations, which has 4 parameters. So basically, this is the fitness distance from the optimum, the ultimate optimum. P is a proportion of this maladaptation that is due to the dominant direction, the one along which we are have a long dominant direction. And alpha is the ratio of anisotropy. So it's really how long compared to thick. And mu is a product of mutation rate, genomic, and effects, variance of effects of the mutation on the traits. So we have 4 parameters, and it's independent of n here because n only affects the load buildup, which is negligible when you have very strong adaptation. So I use that to fit first the early dynamics from the 10,000 generations, first 10,000 generations. I had to repopulate the data from the 2,000 generations because they are based on 10 replicate measures and only the mean and standard deviation is given. So I reproduced the same kind of data set as there is in WISER. And then I used also WISER's data set for the rest and for those times. So this is interesting because doing this is because we have much more time points in the 2000 first generations, but only for one population. So I fitted 2 models. This one, the isotropic model here only, which is really has 2 parameters then. P does not play a role and alpha is 1. And I fitted the power law model used by WISER. So it's a version for Malthusian fitness. So you can see here that both fit the data, but in fact, during this first period, the saturating curve is indeed better than the power law. So the power law doesn't manage as well to take into account what happens. But later, when we look at longer term, then the power law, which is on the right here, does a very good job at fitting the whole trend. But on the other hand, if you allow for anisotropy, now we have an alpha that we also fit, then we give a good fit to the data, but with 4 parameters instead of 2 in the power law case. So what it means here is that basically, because you have anisotropy, basically what happens is that early on you adapt along your dominant direction. So that's your first part here. I represent in log scale the time here. Your first part is adaptation along the dominant direction. And then you move slowly over the other directions where you have much less mutation variance. That's why you have those 2 kind of plateaus here. So we can account for it and we can estimate the alpha from it, which is about 20, so 20 times longer. So the last thing I did then from that, and then I'm through, is I tried to fit mutant data from Elena et al. Of mini transposon inserts, imposing this distribution with an alpha of 21. So I just fitted the dimension for which I had no information, and I scaled the data so that it would correspond to the mean. And because unfortunately the error variance is not available in there, I had to fit it too. And so here is the kind of fit we get. So these are minus the effect. So it's positive, it means deleterious effect. And what's interesting here is that the alpha of 21 is indeed consistent with this particular shape that the DFE had, which had a fat tail here. And that's to say that we can connect the 2 together. Okay, conclude. Well, basically, we can make an optimum model emerge from, we can make an FGM, particular FGM emerge from simple assumptions that include an optimum, but it requires local approximation and this existence of an optimum. But doing this reconciles previous validations of unmutant data of the FGM and long-term trajectories. More generally, I think the lack of convergence in fitness trajectory is not so easy to prove that there is not an optimum. It's not easy. I don't say it is, but it's hard to get definitive proof as we saw. And ideally, a given model should be consistent with a wide diversity of data, not just DLTE, not just random mutants. And for that, we need more accumulation data. And on perspective, so the limits, of course, well, my population genetics was limited here because the true equation is a 2D transport that is hard to solve. This was a diffusive approximation here. the perturbations, we may try to extend the model to avoid this local approximation around the optimum. So have a more, an extra shape of the fitness function. I don't know how it would look like, but we could constrain it to fit mutant data. Of course, there is all this effect of environment, which is really at the core of what people usually are interested in when they use Fisher model. And especially plasticity will change what happens. You can implement sequence data in this. It's quite easy to add a Hamming distance measurement to do. And I wanted to point to a recent model that is also an emergent model from first principles, which is they call the connectedness model. It's only on bioarchive, but this has also the advantage that it can be compared to many types of data, and it would be interesting to see how to use that and to see how to implement them across environments, which is really critical. I thank you. I apologize if I've been too long. And my main collaborators on this work are mainly Lionel Roch and Thomas Lenormand. But I've also worked in these works with Sylvain Gandon, and Ophélie Ronce, Louis Miguel Chevin, and François Hamel. And I thank all the organizers and the people who give their very hardly obtained data to everyone, which is really important.
Thank you very